Okay, I know you're tired. Let's hobble through as much of this as we can so that we are not super behind. Okay, so we're going to start talking about solutions today. And the solution is a homogeneous mixture. So remember that a homogeneous mixture means that it's a mixture where the substances are distributed all the same. It's like got the same composition throughout, which means like if I have a hot coffee, it's the same at the top of the cup or the bottom of the cup or the middle of the cup. That's homogeneous. It's a mixture of two or more substances, and that's different than a compound because a compound is specific ratio between things, like for example, 2 H's to 1 O for water. A mixture can be any concentration. So you would call a cup of coffee a cup of coffee if it was really concentrated or if it was more dilute. Right? If you made your coffee stronger or weaker, you would still say that's coffee, right? So a solution, a mixture is based on indefinite proportions. So like you could have salt water that's a little bit salty or a lot salty and it's still salt water. Versus a compound has to be exactly that right proportion in that molecule, like 2 H's to every 1 O bonded together. And it's a pure substance because each molecule is exactly the same. In a mixture, your molecules might be different from each other. Homogeneous is like the same throughout, versus heterogeneous would be like different pieces. Like a pizza is heterogeneous because it's got different layers and there's different things on it. A salad, heterogeneous, right? Homogeneous is the same throughout. Solutions have two things in them, a solvent and a solute. Solvent is the thing that is doing the dissolving. You can think about it like that. However, it's also by definition present in a higher amount. So the solvent is the thing there's more of. So the solvent for the air that we're breathing right now is nitrogen because that's the substance that makes up 70 something percent of the air in our atmosphere, down here in our atmosphere. Solutes are the things that are getting dissolved. Or we can think about them as present in smaller amounts. So for example, in the air, oxygen would be a solute. Argon is a solute. Carbon dioxide is a solute. Water vapor is a solute. All hanging out in the solvent of nitrogen. Now we think about solutions mostly in chemistry as being solids in liquids, like salt water. Like, oh, you made a solution in lab last semester. Like you put a bunch of solid stuff in those little volumetric flasks. You made solutions. That was usually solid in a liquid. But you can have all different types of phases. So we just talked about gas and gas, like air. You've interacted with gas dissolved in a liquid if you've ever had a carbonated beverage. Gas dissolved in a solid, they give this example like, oh yeah, hydrogen, gas, and palladium, like everybody knows that. I don't know if this is entirely correct, but think about like a pumice stone. It it's got those holes in it because of the gases that were dissolved in the solid, kind of. Maybe not exactly correct in the formation of that. I'm not a geologist, but think about it kind of like that. You can also have liquid and liquid. You've interacted with this. If you ever used isopropyl alcohol or rubbing alcohol, 70% isopropanol, which means it's 70% alcohol and 30% water. It's a solution of two liquids together. A liquid and a solid, mercury dissolved in something else. It's a liquid and a solid. I don't know of other liquid and solid examples besides that. And then a solid and a solid would be like two metals put together, melted together, and then made into a solid, like brass, bronze, stainless steel. Those are all alloys. So those are solid and solids. So there are three different types of solutions, and we'll talk about them mainly with solid liquid. So in chemistry, we do a lot of solid liquid, solid in liquid solutions. Um, so first you have unsaturated. So unsaturated means there are, let me just show you the graph first. So this is coming a lot later, solubility. Okay, so here's a graph I think will help this understanding. So at a certain temperature, you can dissolve a certain amount of a substance. So for example, at 20 degrees C, we can dissolve about 90 grams of glucose in 100 milliliters of water. That's what this graph is showing me. If we try to put 60 grams of glucose in 100 milliliters of water, that would be under the solubility. So that's undersaturated. So we could add more, but we don't. If we added exactly 90 grams of glucose in 100 milliliters of water at this temperature, then that would be saturated. You can't add any more. That's the max you can add at that temperature of that substance. And then we'll talk about what's called a supersaturated solution, where we actually fit more in that gap. So I just wanted to show you that. I think it's helpful just to see that first. For some reason, the textbook put that way far in the back. So imagine that we're adding our solid to our liquid, but we're not adding to the max level of solubility. So we get a solution that looks homogeneous like this, and we could add more, and it would dissolve. We know it's saturated when you add more and you see it not dissolve anymore. So you see how we have some solid just kind of hanging out at the bottom? That means it can't hold anymore at that temperature. So this up here would be a saturated solution. It's holding as much as it can. And if you add more, it's just going to go sink to the bottom, more solute. Now, there is a way to take this and heat it up, increasing the solubility and getting all the solid to actually go into solution. If we heat it up and then we cool it slowly, we can get what's called a supersaturated solution, where we're actually fitting in more than we should be able to at that temperature. So how we do that, and you may do this in lab, is you take a saturated solution, you add more than you should, then you heat it up and dissolve that extra, because now when you heat up a solvent, we're adding space between particles, and so you're essentially stuffing more solute in between the spaces between those particles. And so then we're going to cool it really slowly. So you're going to have the solvent come back to normal, but really slow. If you disrupt it, if you go too fast, if you even just jostle your beaker or something, it might have all that solid just come out of solution like this again. Or if you get a supersaturated solution and you are very careful not to disturb it, if you add a single little bit of that solute, it will disrupt all the other saturated supersaturated solutes, and it will create what's called a nucleation site and allow all the other solute particles to now become solid again. So it will spread, and essentially you will recrystallize your solid. So this is a way also you may use in organic chemistry. It's not exactly the same, but similar to creating a nucleation site to recrystallization is a way to purify a substance. So if I just want the solid, I want it to be pure, I could put it in a solution, heat it up, cool it down, and then provide it with some kind of area to crystallize, and it would be pure of that solute, essentially. So I want you to think about it like this. Let's say you are going to take groceries in from your vehicle, and you want to, it depends on what kind of grocery carrier are you? Are you I have to get everything in one trip? If at all possible, I will literally kill myself to get everything in one trip. Or are you I'll get as many as I can. I'll take as many trips. I'm not going to overdo it. If you're an unsaturated solution, you have bags on your hands, but you could add more. You're taking it easy. You'll say, you know what? I'm not going to do multiple trips. I'm going to do multiple trips, and I'm just going to take it easy. I could add more bags, but I'm not going to. Saturated would be, I have a comfortable amount of bags. I don't think I can handle any more. I've got my max amount of bags in my hands, and now I'll take my groceries in. Super saturated is, I feel superhuman today, and I'm going to try to put bags on, around my head. Each finger has a bag attached to it. I got bags attached to my belt or something. Like, you're just like way oversaturated with bags. If anybody steps in front of you, if your dog or your cat steps in front, you are dropping all those bags, right? If somebody says, here, hold this, you're dropping all your bags. If you have to go to try to get your keys out of your pocket in that situation, you're dropping all your bags. Anything little happens to you, you're really unstable, the bags would drop, which means the same thing as the solute would come out of solution. So that's what's happening here, is that it's just we're adding this one little bit, and now it's all just going to come out because it's not stable in there, because it shouldn't actually have that much at that temperature. When we're talking about dissolving something, we have to consider the interactions. Solute-solute interactions. Let's look at that. So if I had sugar and sugar molecules interacting with each other, they would have intermolecular forces. They're IMFs. Sugar actually has London dispersion forces, dipole-dipole forces, and hydrogen bonding, because it's got some hydrogens attached to some oxygens. What about sodium chloride to sodium chloride, or I guess sodium to chloride? Sodium ion to chloride ion interactions. Those would be ion interactions. So we're thinking about, like, if we want to make sugar water or salt water, the solute-solute interactions we have to consider. Then we have to consider the solvent-solvent interactions. So let's say we're dissolving these in water. So what's the interaction between two water molecules? What's the strongest interaction between two water molecules? Hydrogen bonding. And then we have to consider the solute-solvent interaction. So what's the interaction between sugar and water? Well, if sugar has hydrogen bonding and water has hydrogen bonding, their strongest interaction would be hydrogen bonding. If we were doing like sodium ion to water, that would be ion dipole interactions. Or chloride ions to water, that would be ion dipole interactions. And basically what we're going to have to consider is which of these interactions will be overall stronger. So are we going to be able to take apart the molecules from each other and the water from each other to make these new interactions? So the stronger your solute-solute or solvent-solvent interactions, maybe the less likely we are to dissolve. However, there's another thing that we'll talk about in a second that helps us make this happen, because you may be thinking, well, isn't ionic really strong? Why would it go from ionic to ion dipole? How could we break apart sodium chloride? There's another factor that's going to drive this process. But yeah, you have to break apart the sodium and the chloride. Now, you're not doing lattice energy. It's not turning it into gas, right? But it is it's separating those particles. The water essentially surrounds the sodium and surrounds the chloride, and like rips them apart. Kind of violent. So if you have water, what part of so this is going to be negative, and these would be positive, right? Which ion would the oxygen part of water be attracted to, sodium or chloride? The positive one, sodium. So here we have some interactions here, but it's not, do you think it's just one water in a cup of water? So for every one sodium, I'll bet you've got, and there's actually probably some sort of research number, but we got lots and lots of water. So it's not just considering ion versus ion dipole. It's like, look at how many ion dipoles I get out of this probably, right? It's a lot, and water is literally going to surround it. And so hopefully that gives you a little bit more reason of like, why would it even dissolve? Well, because we probably get a lot of ion dipoles just from breaking that one ionic interaction. And then the same would happen to the chloride. The chloride would have the hydrogens all around it because it's negative. So some intermolecular forces to consider. The ion dipole we've talked about. So the ion attracted to the dipole. Notice that the positive is attracted to the negative. But then there's also these other ion dipole-induced dipole. So let's look at carbon dioxide. How do we get carbon dioxide to dissolve in water? We got to have some sort of attraction between carbon dioxide and the water, but carbon dioxide's non-polar, right? It doesn't have any sort of negative and positive areas. Well, water is so polar that it can actually cause CO2 to be polarized. So we call this a dipole-induced dipole interaction. Just like if you have a substance that's not on its own magnetic, but if you put it near a really strong magnetic field, it can become magnetic. If you have a bunch of negative over here, all your electrons are going to go this way in your carbon dioxide. It's kind of like London dispersion forces. If we have one that happens to be negative on one side, all your electrons are going to kind of flee to the other side. And this causes a momentary polarity in the CO2. And we call this a pure, this is a dipole because it's a polar compound. And then this is an induced dipole because it's not really polar, but it's induced because it's near something that's really strong. Same thing happens here. If you have an ion next to something nonpolar, like how does the hemoglobin, which has an iron ion in it, attract oxygen, which is nonpolar? It doesn't have any charge. How does the iron attract oxygen? Well, when the oxygen gets close enough to the iron, all of oxygen's electrons come to one side. And now you have a negative side of oxygen attracted to the positive iron. So it's an ion-induced dipole interaction. So if you have really strong dipoles or really strong ions close to things that are nonpolar, you can actually make the nonpolar things a little bit polar by inducing that dipole. It's only temporary and it's just a partial charge, but it's enough for you to carry oxygen around in your blood, which is good. And it's enough for you to be able to dissolve CO2 in water. And if you like carbonated beverages, that means that's good for you, right? So it's enough for that. CO2 also gets dissolved in water around, in general, like oceans and that kind of stuff. Oxygen gets dissolved in water. Oxygen and water shouldn't go together because oxygen is very nonpolar, doesn't have any sort of charges for water to be attracted to. But fish breathe oxygen, right? They need oxygen to live. So how do they get oxygen? Induced dipoles. So when we're thinking about this step by step, don't freak out. I know it looks like a Born-Haber cycle, but just think about it. We have our solute and our solvent. They are together. Let's say this one is a solid and this one is a liquid, and they're all together. In order to mix them up, we have to separate our solute. So we have to break solute-solute interactions. So this will be some enthalpy that we have to put in to separate the solute particles from each other. Then we'll have another enthalpy to separate the solvent particles from each other. So to break apart those intermolecular forces. Then, once these two get together, they might actually release some energy because they're more stable together than they were apart. So overall, you might have a process that's endothermic for dissolving your two things together. Or this picture might be even lower and you might have an exothermic reaction. So you might dissolve something and it might be exothermic. But how is this a good thing? Like, I can have something that's overall endothermic. Why would we even put in this much energy to not get enough energy out? The answer to that question is entropy. So yes, enthalpy is part of us predicting how things are going to happen, right? How much energy we got to put in or we get out. But how does anything endothermic ever happen? You have to put in energy to make it happen. Like, why does the universe allow things that take work to you to put in energy for? It's probably because the entropy is good. So I know if you think about this, right? Sodium chloride. You put sodium chloride and water together, it just dissolves. You don't have to heat it up or anything. It just does it. It looks like it's endothermic, right? So it's automatically just taking energy from the environment. Like, why would it do that? It's because when you take two separate things and you mix them up, we get better entropy. Entropy is the measure of how dispersed or spread out the energy is in a system. That's kind of hard to think about. So what we can think about entropy is the measure of disorder. I know some people have called it like the measure of chaos. It's actually the measure of all the different ways in which you can arrange the energy of a system. These are different ways we can put things together are called microstates. Measure of how many different arrangements of energy. And we can think about it as energy, but maybe it's easier for you to see it as particles. That's okay. How many ways can we arrange these two gases separated? This way. One on this side, one on that. We could flip it, we could arrange it with the other gas. We could flip that. There's not really a lot of ways we can arrange and separate out and disperse these particles. How many ways can we rearrange this? Imagine like if I switch these two particles locations, that's one rearrangement. If I switch these two particles, that's one rearrangement. So you can imagine how many possible rearrangements we can get if we mix things up. So same thing happens to my solution. If we have a solute that's the solid, not very good entropy. There's not really a lot of ways I can arrange particles in a solid. If I have a liquid, there are probably more ways I can arrange particles in a liquid because they're more fluid, but still less ways. If I mix them together and the solid particles get dissolved, there's a lot of ways in which I can arrange that. And so that's good entropy, and that's really what drives even endothermic dissolution processes. So naturally a system just becomes dispersed, becomes more chaotic, becomes more disorganized. Entropy is always increasing. If you just leave your room and don't clean it, it is going to get more disorganized just naturally. That's going to happen, right? Even if you leave a room, people who leave houses for a long time put sheets and stuff over the furniture to protect from dust because naturally it will just the wood of the house will break down and it will cause dust and there will be things that come in. If you put a piece of food out on the in the parking lot, eventually it's going to start to decompose, right? It's going to break down into pieces. So entropy is always increasing for the whole universe. So if you go and you make something more ordered, the particles around the thing that you ordered are now more dispersed. So there's always a give and take with entropy. So that's why. So this is really good entropy versus these are really more organized. And so that's why a process like this would happen. By the way, this is called the enthalpy of dissolution. Not sure what your textbook is calling it. It may be enthalpy of solution. I always learned dissolution, but you might see different dissolution, different things as time goes on there. So there's a little rule for what things are going to dissolve together, what things are going to mix together. And the rule is like dissolves like. This is like an oversimplification. So I just want you to be aware of this. This is an oversimplification. It's nice to think about when we're starting out, but when you get up to higher levels of chemistry, you'll learn like, well, this is less of a yes and no question and more of a, well, maybe a little or maybe a little bit more depending on things. So I'll give you an example of that in a second. So two substances with similar magnitude of intermolecular forces or polarities are more likely to be soluble in each other. So for example, carbon tetrachloride and benzene are nonpolar, so they will mix together because they're both nonpolar. All they have is LDF only. So if you're nonpolar, you only have London dispersion forces. So they know how to talk to each other. They go together, kind of. They're similar. Oh, I see you. You're the same as me. You don't have any of that hydrogen bonding or dipole-dipole going on with you. Versus these two, this is methanol and ethanol. See, they would have hydrogen bonding options. So they can talk to each other because now they have a way to interact. The positive of one of these molecules, the hydrogen here is more positive, would connect to the oxygen of that molecule because it's more negative. They're both polar, so they've got those positives and negative sides, and so they know how to interact with each other. But if you have something that's nonpolar, like CCl4 in CH3OH, this would not mix because one is polar and one's nonpolar. They don't really know how to interact with each other. Like you say, oil and water don't mix for this reason. So if it's not miscible, we call it immiscible. If it's mixable, we call it miscible. So if it can mix, we call it miscible. If it can't mix, we call it immiscible. So if it's polar, it'll go with other polar stuff. I want to make a note here. Ionic is like super polar. It's so polar, it doesn't even share electrons anymore. Instead of partial positive, partial negative charges, you have full positive, full negative. So that's why water dissolves a lot of ionic compounds. We call water the universal solvent. It dissolves a lot of stuff because water is pretty polar, so it can dissolve a lot of ionic compounds and polarity, but it doesn't do a good job of dissolving nonpolar stuff like oil. Now, speaking of oil, let me show you an example of a molecule that might look similar to a molecule in oil. Would you consider that molecule to be polar or nonpolar? If you had to pick, polar or nonpolar? You have to pick. If I had to pick, I would say polar because this side is different than this side. Like there's a polarity happening here. But do you think this would dissolve in water? So if you were to put this in water, it actually it's not going to dissolve. Why? This little bit right here is polar, and that matches water's polarity. And also they have hydrogen bonding, right? They both have hydrogen bonding. So water can talk to that side. But this part is all CC and CH bonds. If you have only CC and CH bonds, you are non-polar. So there's a big non-polar section attached here. This is actually what your particles, your molecules of oil look more like. They're not exactly like this, but oil is actually a fatty acid that makes up oils and fats have hydrogen bonding ability. They're not just totally non-polar substances. Like benzene and carbon tetrachloride, non-polar all the way through. This one has a little polar bit to it. But water is like water goes to like shake hands with this molecule and then goes, wait, and looks behind it. And it's like, who is all that back there? Why are you bringing along this whole trail of nonpolar stuff? I don't know. I don't like. Like you inviting a friend over for a party and they bring like a bus full of people you don't know and you don't like. Like, no, you can't come in not with all those people. So these are probably not gonna mix. Likely immiscible. Even though we might describe that molecule as being polar if we have to pick, it's got two sides that are kind of different, which was what we decided as a definition for polar. It's probably not going to dissolve in water. So polarity is not a black and white thing. It's not a yes or no thing. It's a scale. This molecule is more nonpolar than it is polar. So it will probably be happier if we put it with something like benzene, C6H6, or if we put it with something like carbon tetrachloride. Versus these guys who have the hydrogen bonding, they have the same structure as this long one, but they don't have a lot of that nonpolar part. So they're probably okay with water. Yeah, you can come over and you can bring one new friend or two new friends, but you can't bring 16 new friends over, right? So use like dissolves like if you're like answering questions for the most part, but understand that there are limitations to that and it's not quite as clean cut as that in real life. All right, we're going to do this problem. We're going to consider each of these. So you're going to consider bromine. Would it be more soluble in water or benzene? And we're going to do that for each of these. Sodium iodide, water, or benzene. Carbon tetrachloride, water, or benzene. Formaldehyde, CH2O, water, or benzene. So see if you can decide which one of these substances, or for each of these substances, which thing would it dissolve better in? You want to draw Lewis structures. Try. Want to test? This will probably be like circle each of the options. Question like this on a test, you could always test. Shot. Not sure where to start. If you draw the Lewis structure of the thing and see, do you think that's more polar or no? All right, a lot of people got some answers. So bromine is diatomic. And if you have only two elements bonded together, that thing's going to be nonpolar. So it would go better with benzene because benzene is nonpolar. Good. NaI, this, hopefully you did not draw any lines connecting Na and I. We don't draw lines for ionic compounds. You could draw it like that if you want to, but that's ionic, and y'all, ionic is super polar, so it would go with water, like sodium chloride. CCl4. So if I draw my Lewis structure for CCl4, it will look like this. Is this going to be polar or nonpolar? Nonpolar, because if you have the same thing on the outsides of a tetrahedral, it's going to be nonpolar, so it would go better with benzene. And then CH2O would look like this. And this thing is polar because we have a pull up, but we don't have anything pulling down. For this one, we have a pull in all directions equally. Now, it's not technically this T shape, right? It's a 3D tetrahedral shape, but so this one would go with water because it's polar. So simple, just keep it simple. Don't try to overthink it on like a test question like this. Just polar versus nonpolar. All right, we're gonna talk about concentration. Yes. Yes. So lone pairs don't mean that it's polar, right? Because this one has lone pairs and it's non-polar. You mean lone pairs on the center?
Yeah.
So it depends. If you have lone pairs on the center and it's bent, it'll be polar. But if you have lone pairs on the center, like this guy, and it's linear, it would be nonpolar because the lone pairs cancel out. So it is not always lone pairs in the center polar because you have some more complicated geometries that have lone pairs in the center and they're nonpolar. So you kind of have to know the shapes and like your steric numbers, your number of electron groups around it. Like you go back to your notes from last semester. Yeah. Because you got to be good at telling polarity to get the solubility stuff. Good question. All right. Concentration is basically the amount of stuff in the amount of other stuff. Like how much are you dissolving in your total solution or in the amount of solvent? So the first one we have is called molarity, and that is the moles of solute per liter of solution, and we're going to use capital M. It's important to use capital M because there's one coming in the next slide that's lowercase m. You got to make it a nice, very clear capital M. So molarity is moles of solute over liters of solution. Molarity can be written as a conversion factor. So whatever our number of molarity is, we could say that's how many moles in 1 liter. And of course, this would be solute and this would be solution. It's really important to label what you're talking about because we're going to do complicated problems where you got to know, am I talking about the solute or the solvent or the solution? So you can't just put units and just have units being multiplied and divided every which way. You're going to have to label, what is it? Is that the solute? Is that the solvent? Is that the solution? So that means you have to know what those words mean. Question. Yes, so liters of solution, because solution is solute plus solvent. So it's the whole thing. You used molarity last semester when you made stuff in those volumetric flasks, right? You measured the total, you put water until you got to that certain point. That's your liters of solution, essentially, because it had your solvent and your solute in it. Another way we can measure concentration is through a mole fraction. So a mole fraction of some part of your solution, A, would be the moles of that part over the sum of the total moles, all of the moles. What's the fraction of moles? A fraction is a part over a whole. So a mole fraction is the moles of the part over the moles of the whole thing, total moles. I guess technically you could use mole fraction as a conversion factor. So if you knew the mole fraction number, you could use like moles of A equals total moles. No, that wouldn't work. I've never seen mole fraction used as a conversion, so I won't show you, but you will definitely use it. Just know what it is. We use this little fancy X and then the subscript of whatever substance we're talking about. So if it's mole fraction of water, we put H2O there. If it's mole fraction of carbon dioxide, we put CO2 there. Again, a mole fraction is just a fraction of moles. You got to know what a fraction is. A part over a whole. Every fraction is a part over a whole. Next, we have molality. Here's that lowercase m I was talking to you about. It's moles of solute over kilograms of solvent. We can use this as a conversion factor. We can say the number of molality, and we can write it as moles over kilogram, which means we can say the number of moles of the solute is equal to 1 kilogram of solvent. Now, this is measuring the solvent, not the solution. This is sometimes easier in lab because it's like, I don't want to use a volumetric flask. Maybe I just want to weigh out the water and weigh out the salt and then put them together. I'm not concerned with how much space it takes up at the end. Maybe I just need to weigh them both. And that's my molality. Percent by mass is percent. Sometimes we'll write percent by mass. We'll say percent mm. So that means that the mass is the top number and the mass is the bottom number. Essentially, it's the part over the whole mass of the solution, because that's the whole thing. And then we multiply it by 100%. So it's just like a mole fraction, but instead of moles, it's masses. Mass of solute over mass of the whole thing times 100%. And then we get into our parts. So parts per thousand, parts per million, parts per trillion, parts per billion, it's the same thing as percent, but instead of multiplying by 100, you're multiplied by 1,000,000 or 1,000 or 1,000,000,000 or 1,000,000,000. It seems like it's a hard thing, but it's the same as a percent, but instead of times 100, a percent could technically be considered part per 100. But we just put a sign on the end, a percent sign. Part per million, part per thousand wouldn't have a percent sign on it. It would just be like, 10 ppm. It just kind of depends on what you're multiplying it by. The reason we use part per million, part per billion is because sometimes you have really low. So I could give you the percent, but the percent would be like 0.0000012%. So instead you would say 1.2 part per million. Right? It's just a different unit to represent really, really small percentages. So how do we use a percent as a conversion? If I have 5% salt in salt water, for example, and I said it's 5% mass, so it's a mass percent. If I had 100 grams of salt water, let's think about how many grams of salt that would be. So let me ask you a question. What's 50% of 100? 50. What's 75% of 100? 75. What's 10% of 100? 10. Don't subtract it. It's not 90. 10% of 100 is 10. If it's 10% off, you don't go, yay, this $100 thing costs $10. No, it's 10% off. It's $10 off. It's not $90 off, right? So what's 5% of 100? 5. So if you have 100 grams of salt water, it would be 5 grams of salt. What did I do? Assume 100 grams of whatever your whole thing is. And then the number that's your percent just becomes the number that goes with your part. Makes it an easy conversion factor. Yes, you can plug into the algebra formula or whatever, but we got a lot of these kind of things. Y'all have to be able to use them as dimensional analysis because we're going to get real complicated with it. So if you know dimensional analysis is not your forte, I think I put a dimensional analysis practice website in Canvas for Unit 1. Get in there. Or maybe it's in the resources for students. Actually, it's at the very bottom of the first module in Canvas. Get in there this weekend and get good at dragging stuff into dimensional analysis. So what would the ppm for this be? If I said 5 ppm, the concentration of salts in, let me just rewrite it all together. If I said the concentration of the salts in this salt water is 5 ppm, how could I use that as a conversion factor? Well, ppm is out of what? A million, 10 to the 6, or a million, part per million. So if it's, if we could use grams for it, if that's fine. It doesn't tell us part per million, that it just needs to be the same unit on both sides. So we could say if I had 10 to the 6 or a million grams of salt water, how many grams of that would be salt if it's 5 ppm? 5. Because ppm is just like a percent, except it's out of a million instead of out of 100. Doing the same thing, I just changed what number I'm going to use for the whole. Instead of 100, use a million. Now we have a conversion factor we can use for ppm, or we can go and we can now find other things we need. There are other conversions for ppm and ppt and ppb and stuff, but this might be helpful to you. All right, let's practice. I have a solution. It's 170.1 grams of glucose. And I'm making a liter of solution. I tell you the density of the solution is 1.062 gram per milliliter. Tell me what is the molality, what's the percent by mass, what's the part per billion. If you want to try, you could do also molarity. If you wanted to try them all. Stuff. About what you need. You don't have to do molality first if you're kind of scared, but you can do percent by mass first or molarity first. E. What's your solute? What's your solvent? What's your solution? For that, all the formulas for all these in your notes. Didn't write them all down. You're in Canvas. Before class slides for chapter 13. Are you to Right. Stuff that you want to check the progress? Yeah. Good question. So, if you know, you can find the percent. Oh no. So if you can find the percent by mass, you can figure out the mass of the water by itself. Yeah. I'm gonna try doing the percent by mass first before you do the molality. I help you think about how you get the mass of just the water. You know, there's only two things, water and glucose. You know the mass of one thing and the percent of that, and you know that's the other. Okay, skip the molality, like it's a little bit difficult. Try the percent first. Find the grams of the whole thing, the solution. You know the grams of the glucose. What was the grams of the water? Two things in the solution. Glucose, water. One little start with a percent. I want to make it easier.